2.
We are now going to look at the wave equation in 3 dimensions. So everything is depending on the x, y, and z axes. Let's quickly review the Maxwell equations that we're using. All our materials are constants. So there's no variations in the parameters epsilon and mu as a function of the spatial coordinates. And we have no currents J, and we have no charges rho. So we have a simplification of the equations. Divergence of E is equal to 0. Divergence of B, no magnetic charges, 0. Faraday's law stays as is, and Ampere's law with no currents becomes this. Epsilon di t is a representation of the derivative in time of d, which is epsilon E. So now, how do we get waves out of these 4 equations? This is a bit like magic, but we've seen it in 1D. It's just the extension to 3D. Here we go. We take the curl of Faraday's equation on both sides. So curl of the left side, which is this horribly long expression that you can look up in the appendix, and there's a way of deriving it, and I'll give a reference to that in the lecture. It becomes the gradient of the divergence of E minus Laplacian of E. So we'll look at this in more detail after we've set everything up. Now, here's the important step. Curl of the right-hand side of Faraday's law. Well, there it is, minus mu di h di t. Mu is a constant. And also, because everything is smooth, we can interchange the time and space derivatives. That's exactly what we've done here. We pulled this one out and put this one in. So we are differentiating the curl operation. And what we have to do then is look at this part, the left-hand side, equal to this right-hand side, simplify it, and see how we get waves. Notice that divergence of E comes in, and we'll see that by putting it equal to 0 and using the right-hand side of Ampere's law, we're going to get waves.